Right now, close your eyes for just a moment. Imagine standing on a launch pad. It is 3 in the morning. The air smells of metal and fuel. The stars above you are impossibly bright. You are wearing a spacesuit. It weighs more than you expected. Every breath inside the helmet sounds loud, mechanical, alive. You can hear your own heartbeat echoing against the visor glass. Beneath your boots, the platform hums with energy. A rocket stands before you, taller than a cathedral. Vapor curls off its surface like breath in winter. This machine was built for one purpose only. It was built to take you to Mars. You have trained for years. You have said goodbye to everyone you love. You wrote letters you hope they never need to read. And now, standing here, the desert wind pressing against you, something becomes very real. If you step inside this rocket, you will likely never return to Earth. Not because of a malfunction, not because of some dramatic disaster. The reason is quieter than that, more permanent, more woven into the very nature of what Mars does to a human body. This is not science fiction. This is not a warning from a movie. The finest researchers on this planet have studied the question carefully, and their conclusions are unsettling in the gentlest possible way. Mars changes you. The journey changes you. The gravity changes you. The radiation changes you. And after enough time, your body will no longer belong to Earth. You will have become something new. Picture this. You arrive on Mars after 7 months of travel. You step onto rust-colored soil. You look up and see a sky that is not blue but a pale butterscotch. 2 tiny moons drift overhead like distant stones. You feel lighter. Mars has only 38% of Earth's gravity. Your muscles begin to relax in ways they never have. Your spine stretches. Your heart pumps differently. Every cell starts adapting to a world that is not home. And that adaptation is a one-way door. Here is the paradox that science struggles to explain fully. We can send a human to Mars. We have the engineering. We have the rockets. We nearly have the life support. But bringing that human back healthy may be impossible. Not difficult. Not expensive. Possibly impossible. The familiar detail is this. We have already sent robots to Mars. We have driven rovers across its surface. We have photographed its canyons and tasted its dust with instruments. Mars feels close. Mars feels almost ready. Now the twist. The human body is not a rover. It cannot be switched off during transit. It cannot ignore radiation. It cannot pause its bones from weakening. It is an ancient biological machine designed for one specific planet. And that planet is not Mars. Tonight, we will follow the quiet science behind humanity's greatest voyage. We will trace the history of how we first dreamed of reaching the red planet. We will examine what happens to bone, muscle, and mind across millions of miles. We will explore the radiation that passes through spacecraft walls like they are made of paper. We will measure the gravity that slowly reshapes a skeleton. We will listen to the psychology of isolation that no training can fully prepare you for. And we will ask the question almost nobody is willing to answer honestly. If we send people to Mars, are we asking them to give up their ability to ever live on Earth again? Are we asking for volunteers who understand the contract they are signing? A contract written not in ink, but in biology? Tonight, we go into the gap that enthusiasm alone cannot bridge. This is not a story designed to frighten you. It is designed to honor the truth. Because the people who will go to Mars deserve our honesty. They deserve to know what the silence between the stars actually costs. So settle in. Let your breathing slow. Let the weight of the day fall away from your shoulders. We have a long and beautiful journey ahead of us. From ancient stargazers to modern launch pads. From mythology to medicine. The night is vast. The story is patient. And Mars, glowing like an ember on the horizon, is waiting for us to understand what it truly means to visit a world that does not want to let you leave. This is the documentary contract. We will not rush. We will not sensationalize. We will follow the evidence wherever it leads, even into uncomfortable places, even into the quiet spaces where wonder and grief hold hands. By the end, you will understand something profound about what it means to be human, about what our bodies remember, about what our bones expect, and about why the bravest journey in history may also be the most permanent. Let us begin where all great stories begin, with someone looking up at the night sky and wondering if that pale red light could ever be reached by human hands. The answer, it turns out, is yes. But reaching it and returning from it are two entirely different promises. Chapter 2. Why this matters to you right now. You might wonder why this matters tonight. You are not an astronaut. You are not planning to board a rocket. You are lying in the dark, perhaps letting your mind drift towards sleep. Mars feels very far away, but this story is not really about Mars. Not entirely. It is about the human body and what it needs to survive. It is about the quiet contract between your bones and the earth beneath you. Right now, gravity is holding you. It is pressing your body gently into your bed. Your muscles are resting against it. Your spine is decompressing after a long day. This force, so constant you never notice it, is keeping you whole. Everything about you evolved for this specific pull. Your heart is the exact right strength to push blood upward against Earth's gravity. Your bones are precisely dense enough to support your weight on this world. Nothing is accidental. Nothing is accidental. This is what makes the Mars question so deeply personal. It is not about rocket fuel or landing gear. It is about whether a body shaped by millions of years on one planet can survive on another. And the answer touches something existential, something comforting, actually. Because understanding why Mars might not give us back also means understanding how perfectly we belong here. Every breath you take tonight is possible because of an atmosphere that took billions of years to form. The oxygen in your lungs was forged inside dying stars, collected by Earth's gravity and held in place by a magnetic field generated deep within our planet's molten core. You are breathing the gift of a living world. Mars does not have this gift. Its atmosphere is thin, 95% carbon dioxide. The air pressure on its surface is less than 1% of Earth's. If you stood on Mars without a suit, your blood would begin to boil. Not from heat, from the absence of pressure. The boiling point of liquid drops when pressure drops. Your body's fluids would vaporize at the surface. This would happen in seconds. Mars is beautiful, but it is not gentle. So why do we want to go? Because wanting to explore is one of the oldest parts of being human. Before we had language, we had curiosity. Before we had maps, we had footprints leading toward the unknown horizon. We are a species that walks forward. And Mars represents the next horizon, the most ambitious step any civilization has ever attempted. Not a journey across an ocean or a continent, but across the void between two worlds. 55 million kilometers at closest approach. This matters because the people who volunteer for this journey will carry all of humanity's hope with them. They will represent every dreamer, every scientist, every child who ever pointed at a red dot in the sky. They deserve the truth about what awaits them. This documentary is not here to discourage exploration. It is here to illuminate it, to hold a gentle lantern over the medical realities, the psychological weight, and the biological transformations that a Mars mission demands. There is profound beauty in understanding limits. A river is beautiful partly because it has banks. A life is precious partly because it ends. And a journey to Mars is magnificent partly because it asks for everything. We are not trying to build fear tonight. We are trying to build understanding. The kind of understanding that lets you appreciate the courage required. The kind that makes you look at astronauts differently, with deeper respect. Because when someone boards a Mars-bound spacecraft, they are not just leaving a planet. They are leaving the only environment their body has ever known. They are trusting that human ingenuity can substitute for 4 billion years of planetary evolution. That is an extraordinary act of faith. And here is where it becomes a sleep-safe meditation for you. Lying here tonight, you are surrounded by everything your body needs. The air is right. The gravity is right. The pressure is right. You are home. There is comfort in that knowledge. Deep, bone-level comfort. The kind of comfort that astronauts on Mars will ache for. The kind they will dream about during long Martian nights that last almost exactly as long as ours. Mars rotates once every 24 hours and 37 minutes. Its day is so close to Earth's that it feels like a cosmic echo, a whisper of similarity inside a vast ocean of difference. That near match is both a comfort and a cruelty, because it makes Mars feel familiar. It makes humans feel like they could live there. And familiarity can be dangerous when it masks how alien a world truly is. In the chapters ahead, we will walk through the history of Mars observation. We will meet the ancient astronomers who first tracked its wandering path across the sky. We will watch telescopes grow larger and imaginations grow wilder. We will follow the science from mythology to medicine, from Ptolemy to modern physiology labs, where researchers simulate the effects of low gravity on human tissue. The story is long. The story is patient. And so are we. Take a slow breath. Let it out. Feel the gentle pull of Earth beneath you. That invisible hand that has held every human who ever lived. It is holding you now. It will hold you all night. And as we travel together toward Mars, remember this. Understanding the cost of a journey does not diminish its beauty. It deepens it. Every sacrifice illuminated makes the courage brighter. Every risk acknowledged makes the dream more real. Chapter 3. When we first looked up and saw a wanderer, long before anyone understood what Mars was, they noticed it moved differently. Most stars held their positions night after night, fixed like jewels sewn into dark fabric. But a few lights wandered. They drifted slowly against the backdrop. The ancient Greeks called them planetes, wanderers, and among these wanderers, one stood out. It glowed with a color unlike any other point in the sky, a deep, rusty amber, sometimes bright, sometimes faint, always unsettling. That was Mars. 5,000 years ago, Babylonian astronomers tracked its path with remarkable precision. They carved its movements into clay tablets. They noticed something strange. Sometimes Mars appeared to move backward across the sky. It would reverse direction, then resume. This retrograde motion baffled ancient observers. It seemed impossible. How could a celestial light change its mind? They had no framework for orbits or planetary mechanics. So they did what humans always do with mystery. They made stories. To the Babylonians, the Red Wanderer was Nergal, god of war and plague. Its crimson color reminded them of blood, of battlefields, of the fever that takes soldiers in the night. Mars was a warning written in light. The Egyptians saw it too. They called it Herdesher, the Red One. They associated it with chaos, with the desert depressed against the edges of their Green Nile Valley. Mars was the wilderness beyond safety. And the Romans, of course, named it after their own god of war. Mars, the name we still use, carried forward across millennia, from Iron Age temples to mission control rooms, an unbroken thread of human fascination. But naming something is not the same as understanding it. For centuries, the best minds believed Earth sat at the center of everything. The sun, the planets, the stars all revolved around us. This geocentric model, championed by Ptolemy around 150 AD, explained most observations reasonably well. It required complicated additions, though. To account for Mars's backward motion, Ptolemy introduced epicycles. Small circles within larger circles, wheels within wheels. The math worked, but the elegance was missing. Nature was trying to tell us something simpler. It took over 1,000 years for someone to listen. In 1543, Nicolaus Copernicus published a radical idea. What if Earth was not the center? What if the Sun was? What if all the planets, including Earth, orbited around it in great circles? Suddenly, retrograde motion made sense. Mars appeared to move backward because Earth, on a faster inner orbit, periodically overtook it. Like a car passing a slower vehicle on a highway, the slower car seems to drift backward against the distant landscape. Simple, elegant, true. Copernicus did not have a telescope. He worked with careful observation and mathematical courage, but his model was still imperfect. He assumed orbits were perfect circles. They are not. That correction would come from an unlikely partnership. Tycho Brahe was a Danish nobleman with a golden nose. He had lost part of his real nose in a duel and wore a prosthetic made of metal. He was also the most precise astronomical observer of his era. Brahe spent decades recording planetary positions with extraordinary accuracy. His instruments were mechanical, not optical. But his measurements of Mars were so precise that they would change everything when placed in the right hands. Those hands belonged to Johannes Kepler. Kepler was a German mathematician, brilliant, poor, and slightly mystical. He believed the universe was built on geometric harmony. Brahe hired him, somewhat reluctantly, and gave him the problem of Mars. It was the hardest planetary orbit to fit. Kepler struggled for years. He tried circle after circle. None matched Brahe's data for Mars. The errors were tiny but persistent. 8 arc minutes of discrepancy. Most astronomers would have ignored it. Kepler could not. He trusted the data. And so he tried something radical. What if the orbit was not a circle at all? What if it was an ellipse? A slightly squashed oval with the sun at one focus? He tested it against the numbers. It fit perfectly. This was Kepler's first law. Planets orbit in ellipses. It was born directly from the study of Mars. The red planet, the troublemaker, the wanderer that refused to follow perfect circles, had just rewritten the laws of the cosmos. Think of it this way. Imagine trying to draw a perfect circle around a moving point of light, and no matter how carefully you draw, the light always drifts outside your curve. The circle is wrong. The light knows a different shape. Kepler found that shape, and in doing so, he unlocked the grammar of planetary motion. His 3 laws would later form the foundation upon which Isaac Newton built the theory of gravity itself. Mars was the key that turned the lock. By the early 1600s, Galileo had pointed a telescope at Mars. He saw a tiny reddish disk, no details, no canals, just a dot with color. But seeing it as a disk rather than a point confirmed something important. Mars was a world, a place. Not a god, not a warning, not a symbol of war. A real sphere hanging in space, reflecting sunlight, following an elliptical path around the same star that warms our faces each morning. That realization changed everything quietly. If Mars was a world, could it have mountains, weather, water, life? These questions would take centuries more to investigate, but they had been planted like seeds in the fertile ground of human curiosity. Chapter 4. The distance that changes everything. Now let us talk about distance. Because distance is where the dream of Mars begins to reveal its cost. And the numbers, when you sit with them quietly, are both beautiful and sobering in equal measure. Earth orbits the Sun at an average distance of about 150 million kilometers. Astronomers call this one astronomical unit. It is the ruler we use to measure everything else in our solar system. Mars orbits farther out. Its average distance from the Sun is about 228 million kilometers. But because both planets are moving along their own elliptical paths, the distance between them constantly changes. It breathes like something alive. At its closest, during a period called opposition, Mars can be as near as 55 million kilometers. At its farthest, when the Sun stands between us, it can be over 400 million kilometers away. The gap is enormous and restless. Let us make this real. Light is the fastest thing in the universe. It travels at roughly 300,000 kilometers per second. A beam of light leaving Earth during opposition would reach Mars in about 3 minutes. During the farthest separation, that same beam would take over 22 minutes. This means a radio signal, a simple hello, sent from Earth to a Mars base would arrive anywhere from 3 to 22 minutes later. Every single time. Imagine calling someone you love. You say, hello. Then you wait. 3 minutes, 10 minutes, 22 minutes. Then their response begins its own long journey back. A simple conversation could take nearly an hour for just 2 exchanges. This is not a technical problem with our radios. This is a law of physics. Nothing can travel faster than light. No clever engineering, no future technology, no amount of funding can shorten this delay. The universe has a speed limit. Now think about emergencies. A medical crisis on Mars, a habitat breach, a landing failure. Mission control on Earth would not even know it happened until minutes after. Their instructions would arrive minutes after that. Help is always delayed. This communication delay is the first invisible wall between Mars and Earth. It means a Mars crew must be self-sufficient in ways no human expedition has ever been. They cannot call for real-time help. They are profoundly, beautifully alone. But distance is only the beginning. Let us zoom out further. Our entire solar system, Sun, and all its planets sits inside a galaxy called the Milky Way. The Milky Way contains roughly 200 billion stars. Our Sun is just one ordinary yellow star among them, located partway along a spiral arm. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. The numbers become so large they lose meaning. If the distance from Earth to Mars is a single step across your living room, then the distance to Proxima Centauri is a walk from New York to Los Angeles. And that is just the nearest star. The galaxy stretches far, far beyond. The Milky Way itself is roughly 100,000 light-years across. And beyond it lie billions of other galaxies, each containing billions of stars, stretching outward in every direction for at least 93 billion light-years of observable universe. We are staggeringly small. And yet, Mars is close. In cosmic terms, Mars is our next-door neighbor. It is practically touching us. If we cannot master the journey to a world this near, then every other star, every other galaxy, every other dream remains forever out of reach. This is why Mars matters beyond Mars. It is the test. The first true examination of whether a biological species born on one world can survive the crossing to another. Not robots, not probes, living, breathing, fragile human beings. So let us bring the scale back down to something personal. You are lying here tonight on a planet spinning at roughly 1,600 kilometers per hour at the equator. You do not feel it. Earth is simultaneously orbiting the Sun at about 107,000 kilometers per hour. You do not feel that either. And the entire solar system is orbiting the galactic center at roughly 800,000 kilometers per hour. You are moving at incredible speeds in multiple directions, and yet you feel perfectly still. Gravity and inertia conspire to create stillness. That stillness is an illusion of belonging. Your body has calibrated itself so perfectly to these motions that they are invisible. This is what 4 billion years of evolution produces. A species so precisely tuned to its home that home becomes invisible. Mars will make home visible again. Every astronaut who lands there will suddenly feel what they have lost. The gravity will be wrong. The horizon will be too close. The sky will be the wrong color. The silence will be a new kind of heavy. And their bodies, those ancient instruments calibrated for Earth, will begin to change. Bones will weaken. Muscles will atrophy. Eyes may shift in shape. The cardiovascular system will remodel itself for a world it was never designed to inhabit. These changes are not speculation. We have data. We have evidence from astronauts who spent months aboard the International Space Station in microgravity. And what we have learned is both fascinating and deeply concerning. But that evidence, those medical studies, the slow biological transformation that begins the moment you leave Earth's gravity well, all of that belongs to the next part of our story. And it is perhaps the most important part, because this is where the dream meets the body, where ambition meets biology, where the human desire to explore confronts the quiet, patient limits written into every cell we carry. The conversation between wonder and fragility. Before we go there, let the scale of tonight's journey settle gently into your mind. From Babylonian clay tablets to Kepler's ellipses, from Ptolemy circles to the speed of light, from your living room to the edge of the observable universe, and back again to one small red world, 55 million kilometers away at its closest, waiting for us with rust-colored soil and a thin, cold atmosphere that cannot sustain a single unprotected breath. Beautiful, harsh, patient, almost impossibly close. The distance is not the hardest part. We can cross the distance. We have rockets powerful enough, trajectories efficient enough, and engineers clever enough to deliver human beings to the surface of Mars within the next 2 decades. The hardest part is what comes after landing. The hardest part is what Mars does to the body that dared to arrive. What low gravity does to bones that expected Earth. What cosmic radiation does to cells that evolved under the protection of a magnetic field Mars lost billions of years ago. The hardest part is the return. And as the evidence will gently reveal in the chapters ahead, the return may not be possible. Not because we lack the technology to launch a rocket from Mars, but because the human body, after enough time on another world, may no longer survive the homecoming. That is the quiet truth waiting for us just ahead. Rest here for a moment. Let the stars turn slowly overhead. Let the numbers settle like dust on a Martian plane. We have traveled far tonight, and there is so much more to discover. When you are ready, we will step into the medical evidence. We will meet the scientists who study what space does to human tissue. We will learn why bones dissolve, why eyes change shape, and why the heart forgets the weight of Earth. The next chapter begins where your body ends and the universe takes over. Chapter 5. The body that disagrees with the dream. Here is where the story turns. Where the dream of Mars meets the quiet rebellion of human biology. Because everything we have learned from spaceflight so far contains a contradiction that no amount of enthusiasm can smooth away. The contradiction is this. We know how to get humans to Mars. The engineering is nearly solved. Rockets exist. Trajectories are mapped. Life support systems improve each year. The problem is not getting there. The problem is what happens after. And the evidence comes from a place much closer to home. The International Space Station orbits Earth at roughly 400 kilometers altitude. Astronauts live there for months at a time. Some have stayed for nearly a year. They float in microgravity. They exercise 2 hours every day on specially designed machines. They eat carefully planned meals. They receive the best medical monitoring humanity can provide. And still, their bodies change in ways we cannot fully reverse. Let us start with bones. On Earth, your skeleton constantly rebuilds itself. Old bone is broken down by cells called osteoclasts. New bone is built by cells called osteoblasts. This process is balanced by gravity. The mechanical stress of standing and walking signals your bones to stay strong. Remove gravity, and the signal vanishes. Osteoclasts keep working. Osteoblasts slow down. The result is a net loss of bone density, roughly 1 to 2% per month in weight-bearing bones. Hips, spine, legs. The architecture slowly hollows. A 6-month stay on the space station can cost an astronaut 5 to 10% of their bone density, A round trip to Mars, roughly 7 months each way plus surface time, could mean 18 months or more of bone loss. Some of that loss can be recovered on Earth, but not all. Studies of returned astronauts show that even after years of rehabilitation, some bone density never returns. The skeleton remembers its time in reduced gravity. The record is written inside you. Now here is the anomaly that concerns researchers most. Mars has gravity, 38% of Earth's, so bones would experience some mechanical loading. The question is whether 38% is enough to halt the decline. And the honest answer is that nobody knows. We've never tested it. We have data for microgravity. We have data for full Earth gravity. We have almost nothing for the space between. 38% exists in a blind spot of human physiology. It is an unexplored territory inside our own bodies. Some models suggest that Martian gravity would slow bone loss significantly. Other models suggest it would merely slow it, not stop it. The difference matters enormously. Slowing a decline is not the same as preventing one. If bones continue to weaken on Mars, even slowly, then after a year or two on the surface, an astronaut's skeleton might be too fragile to withstand Earth's gravity upon return. The homecoming would break them, literally. And bones are only one chapter of the body's disagreement. Muscles atrophy in reduced gravity. The heart, which is a muscle, remodels itself. In microgravity, astronauts' hearts become more spherical. They lose mass. They pump differently. On the space station, this is manageable. On Mars, over years, it is an open question. Fluid shifts present another concern. Without full gravity pulling blood and water downward, fluids accumulate in the upper body and head. Astronauts report puffy faces and congested sinuses, but the deeper effect is on the eyes. A condition called spaceflight-associated neuroocular syndrome has been documented in over half of long-duration astronauts. The optic nerve swells. The shape of the eyeball changes. Some astronauts return with permanently altered vision. They need new glasses for the rest of their lives. Would Martian gravity prevent this? Perhaps, perhaps not. The 38% question hangs over every organ system, every muscle, every fluid compartment, every cell that relies on gravitational cues to function correctly. We are building a mission to a world whose gravity exists in our physiological blind spot. Here is a quiet moment to pause and breathe. Notice how your body feels right now. The weight of your arms, the gentle pressure against your back. This is Earth holding you. Every system inside you expects exactly this much force. Take that expectation and reduce it by 62%. Hold it there for 2 years. Then, ask your body to readapt to full gravity. Ask your thin bones to support your weight. Ask your weakened heart to pump blood upward against a force it has forgotten. That is the return trip. And that is the contradiction. We celebrate the going. We plan the landing. We design habitats and rovers and greenhouses. But the return is where biology raises its quiet hand and says, I was not consulted about this plan. Now layer in radiation. Earth's magnetic field deflects most cosmic radiation. The space station sits within this protective bubble, called the magnetosphere. Astronauts there receive elevated radiation, but they are still partially shielded. Mars has no global magnetic field. It lost its dynamo billions of years ago. The surface is bathed in cosmic rays and solar particle events. Spacecraft walls provide some protection during transit. But on Mars, the thin atmosphere blocks very little. Cumulative radiation exposure increases cancer risk, damages the central nervous system, and may accelerate cognitive decline. Studies on mice exposed to simulated cosmic rays show memory impairment and increased anxiety. The brain does not like being bombarded by heavy ions. A Mars crew would accumulate radiation doses far exceeding current limits for astronauts on the space station. The long-term health consequences are modeled but not fully understood. We are extrapolating from limited data into a territory of genuine uncertainty. And uncertainty in medicine is not neutral. Uncertainty means risk. It means we cannot promise safety. We can only promise that we have done our best with what we know, and what we know has gaps large enough to fly a rocket through. This is not a reason to abandon the dream. It is a reason to look at the dream with both eyes open, to see it clearly, to honor the people who will carry it forward by refusing to minimize what they will face. The body has spoken through every astronaut who has returned from space with thinner bones, altered vision, and a heart shaped differently than when they left. The evidence is not ambiguous. It is consistent, repeated, and documented across decades. What remains unknown is whether Mars itself, that 38% gravity, that thin atmosphere, that absent magnetic field, will allow the body to stabilize or continue to decline. And that single unknown contains the entire question of return. Stay with this uncertainty. Do not rush past it. Let it settle, because the next part of our journey addresses the stories people tell to make this uncertainty disappear. The myths, the shortcuts, the reassurances that feel good but may not survive contact with reality. Chapter 6. The comfortable lies we tell about Mars humans are storytellers. When reality becomes uncomfortable, we reach for narratives that soothe. This is not a flaw. It is a survival mechanism. Stories help us process fear, manage uncertainty, and maintain the courage to act in the face of the unknown. But sometimes the stories we tell ourselves about Mars are not entirely honest. They are not lies in the malicious sense. They are hopes dressed as facts, optimism wearing the costume of evidence, and they deserve gentle examination. Let us start with the most common one. We will figure it out when we get there. This phrase appears in nearly every conversation about Mars colonization. It carries a beautiful confidence. It echoes every great expedition in human history. Explorers always adapt. Humans always find a way, and there is truth in it. Humans are extraordinarily adaptable. We have colonized deserts, Arctic tundra, ocean islands, and high-altitude plateaus. We have built cities in places that seem inhospitable. Adaptation is written deeply into our species. But every previous adaptation happened on Earth, within Earth's gravity, under Earth's magnetic shield, breathing Earth's atmosphere. The environmental parameters varied, sometimes dramatically, but the fundamental physical forces remained identical everywhere on our planet. Mars is not a harsh corner of Earth. It is a different world with different physics pressing against every cell. The adaptation required is not cultural or technological. It is biological. And biological adaptation operates on timescales of thousands to millions of years. We will not evolve to handle Mars in a single generation. The next comforting story involves artificial gravity, spinning spacecraft, centrifuges on the Martian surface. Surely we can simulate Earth's gravity mechanically and protect the body during transit and surface stays. This is a legitimate engineering concept. Rotating habitats could theoretically generate centrifugal force that mimics gravity. But the practical challenges are immense. A spacecraft would need to be very large or spin very fast to produce meaningful artificial gravity. Fast rotation causes problems of its own. The Coriolis effect creates disorienting sensations. Moving your head while spinning makes you nauseous. Smaller habitats with faster spin rates produce stronger Coriolis effects. Larger habitats are enormously expensive to launch and assemble. No spinning habitat has ever been built or tested in space, not even at small scale. The concept exists beautifully in physics equations and science fiction films, but it has 0 hours of operational testing with human occupants in actual spaceflight conditions. Presenting artificial gravity as a solved problem is premature at best. Here is another story that circulates widely. Mars radiation is manageable. Just build underground. Cover your habitat with regolith. Use water shielding. The solutions are straightforward. This is true, partially. Shielding works. Underground habitats would reduce radiation exposure significantly, but shielding protects you while you are inside the shelter. Mars exploration requires going outside, working on the surface, maintaining equipment, constructing new habitats. Every hour outside the shelter is an hour of elevated radiation exposure. A fully underground life is not exploration. It is imprisonment in a cave on another world. And the transit itself, 7 months each way, offers minimal shielding options. Spacecraft cannot carry enough mass to block cosmic rays effectively. Some radiation types, heavy ions called HZE particles, actually produce secondary radiation when they strike shielding material, creating showers of new particles inside the spacecraft. More shielding can sometimes mean more secondary radiation. The physics is counterintuitive and not fully solved. Let us pause here. Take a breath. Feel the air fill your lungs without effort. You are breathing an atmosphere held in place by gravity and protected by a magnetic field. Both of these things are gifts you did not have to build. Now, perhaps the most seductive myth of all. Elon Musk will solve it, or NASA will, or China, or some brilliant future engineer. The myth of the singular savior. The idea that one person or one organization will crack every problem through sheer will and funding. This is not how biology works. You cannot disrupt your way out of bone density loss. You cannot innovate past the speed of light to eliminate communication delays. Some problems are not engineering problems. They are physics problems. They are biology problems. And biology does not negotiate. The people leading Mars mission planning know this. The serious scientists at NASA, ESA, and private space companies publish papers acknowledging these risks openly. The gap is not in what experts understand. The gap is in how the public conversation represents the challenges. Popular media often presents Mars colonization as inevitable, imminent, and essentially solved. Viral videos show rendered cities under glass domes. Social media posts show terraformed landscapes with blue skies and flowing water. These images are beautiful. They are also separated from reality by centuries of technology that does not yet exist. Terraforming Mars, making its atmosphere breathable, would require releasing enormous amounts of greenhouse gases, rebuilding atmospheric pressure, and somehow restarting a magnetic field. Current estimates for even partial terraforming range from hundreds to thousands of years. Some physicists argue it may be impossible entirely. None of this means we should not try. None of this means Mars is not worth visiting. But there is a difference between visiting and living. A difference between exploration and colonization. And that difference is measured in what the human body can endure. Another common misconception involves the comparison to early ocean voyages. People say that sailing across the Atlantic was once considered impossible and suicidal, and they were wrong. So perhaps we are wrong about Mars too. The comparison is poetically appealing but scientifically misleading. Sailors crossing the Atlantic faced storms, scurvy, and navigation challenges. But the air was breathable. The gravity was identical. The water, while dangerous, could sustain life. They never left the biosphere. Mars travelers would leave the biosphere entirely. They would exist in artificial life support for years. Every breath manufactured. Every drop of water recycled. Every calorie grown or carried. The margin for error is not thin. It is nearly non-existent. Honoring the dream means telling the whole truth about it. Not the comfortable version. Not the version that fits in a tweet or a promotional video. The version that includes bone loss and radiation and communication delays and psychological isolation. Because the volunteers who go to Mars will face all of it. They deserve a culture that prepared them honestly, not one that handed them optimism and called it preparation. Rest with this for a moment. Let the myths settle gently. They are not enemies. They are the stories we tell because we love the stars. But love and honesty are not opposites. The deepest love demands the clearest sight. And the clearest sight reveals something we must now face directly. Chapter 7. What changes if nobody comes home? Now, we arrive at the stakes. The real ones. Not the technical specifications or the medical data, though those matter enormously. The stakes that live in the space between a person and everyone they have ever loved. If going to Mars means never coming back, then the mission profile changes fundamentally. It is no longer an expedition. It is an emigration, a permanent departure, a farewell that does not contain the word temporary anywhere inside it. This changes who volunteers. This changes how we select crews. This changes what we build on Mars and what we promise to the people we send. Every assumption about Mars missions currently rests on the premise of return. Remove that premise and everything shifts. Consider navigation first. Current Mars mission plans involve carefully timed launch windows. Earth and Mars align favorably roughly every 26 months. Miss the window, and you wait over 2 years for the next opportunity. Timing is everything. Return missions are planned around these windows. The crew lands on Mars, conducts research for a limited period, and launches back toward Earth when the planets align again. Total mission time is estimated at roughly 2 to 3 years. But if return becomes medically inadvisable after extended surface time, then the window concept changes. There is no rush to leave. There is no alignment to catch. The crew stays permanently. The mission becomes something entirely new. It becomes a settlement. And a settlement needs different things than an expedition. An expedition needs enough supplies to last until return. A settlement needs the ability to produce supplies indefinitely. Food, water, oxygen, building materials, medicine, spare parts, all manufactured on Mars, from Mars. This is called in situ resource utilization, using what Mars provides to sustain life. The concept is real and being actively researched. Mars has water ice at its poles and beneath its surface. Its atmosphere, though thin, contains carbon dioxide that could be processed. Its soil contains minerals, not all useful, some toxic. Perchlorates in Martian regolith are harmful to human biology. They would need to be removed before soil could grow food. Every resource on Mars comes with conditions attached. Building a self-sustaining settlement on Mars is not a weekend project. It is a generational endeavor. It requires decades of infrastructure development, likely by robots first, before humans could arrive with any hope of long-term survival without resupply. And resupply from Earth is expensive beyond comprehension. Every kilogram sent to Mars costs thousands of dollars. A single supply mission takes 7 months to arrive. If something critical breaks between supply windows, the crew must solve the problem alone. This is where the psychological stakes become overwhelming. Imagine knowing you will never see Earth's blue sky again, never feel rain on your face, never hear birdsong outside your window, never hug someone who is not one of your small crew. Studies of isolated populations on Earth, Antarctic research stations, submarine crews, remote island communities show consistent psychological effects: depression, interpersonal conflict, withdrawal, cognitive dulling. And these populations know they will eventually go home. Remove the knowledge of return, and the psychological landscape changes in ways we have never studied. No human being has ever faced permanent, irreversible separation from Earth. We have no data. We have no model. We have only imagination and concern. Some researchers propose that the first Mars settlers would need to be selected partly for psychological resilience to permanent separation. People who can build meaning and community in isolation. People who can grieve what they have lost and still function. That is an extraordinary thing to ask of a human being. And yet there is something else here too. Something that deserves space in this conversation. something beautiful alongside the concern, because there will be volunteers. There will be people who hear all of this and still say yes. That choice, fully informed, freely made, is one of the most profound expressions of human courage imaginable. To leave everything familiar, knowing the cost, knowing the permanence, and to walk forward anyway for the sake of the species. This is where the meaning stakes live. If Mars settlement succeeds, it means humanity becomes a multi-planetary species. It means that no single catastrophe, asteroid, pandemic, nuclear war, climate collapse can end the human story entirely. A backup exists. A second branch. A hedge against extinction. The philosophical weight of this is enormous. Every child born on Mars would be the first generation of a new kind of human, shaped by different gravity, seeing different stars, breathing manufactured air, knowing Earth only as a bright point in their evening sky. Over generations, their bodies would adapt to Martian conditions. Their bones would calibrate to lower gravity. Their cardiovascular systems would optimize for a different pull. They might grow taller. Their muscles might develop differently. Their eyes might change. Given enough time, thousands of years perhaps, the descendants of Earth humans living on Mars might become biologically distinct enough that returning to Earth would be not just difficult but genuinely dangerous. Two branches of humanity, separated by gravity. This is speculative, but it rests on solid evolutionary principles. Organisms adapt to their environment over generations. Separate two populations in different environments long enough, and they diverge. This is how species form. It has happened billions of times on Earth. Mars could be the beginning of human speciation. Not in our lifetimes, not in our grandchildren's lifetimes, but in deep time, the kind of time the universe thinks in, the kind of time that turns fish into philosophers. Lie with that thought for a moment. Let it expand. Somewhere in the distant future, two kinds of humans might exist. Earthlings and Martians. Cousins separated by 55 million kilometers and thousands of years of divergent evolution. Both human, both different. The measurement of time itself would change. A Martian year is 687 Earth days. Seasons last twice as long. Calendars would diverge. Holidays would lose synchronization. Slowly, over centuries, two cultures would develop that share an origin but not a present. The telescopes are already being designed that could watch this unfold. Instruments that could study Martian settlements from Earth orbit. Relay satellites that could maintain communication, delayed but persistent, between two branches of civilization growing slowly apart. This is the largest human story ever contemplated. Larger than any war, any empire, any migration. It is the story of a species learning to exist in two places at once. And it begins with a single irreversible decision. Someone stepping onto a rocket and not coming back. We are approaching the heart of this documentary now. The medical evidence laid bare. The psychological research examined without flinching. The engineering solutions weighed honestly against the problems they claim to solve. The math of radiation and bone and time. But before we go there, settle deeper into wherever you are resting tonight. Feel the comfort of a world designed for you. Let gratitude for this thin atmosphere, this precise gravity, this spinning magnetic heart beneath your feet fill you quietly. Because what comes next requires us to look directly at the most detailed evidence we have. The astronaut studies, the twin experiments, the cellular research, the data that shows, measurement by measurement, what leaving Earth does to the body that dared to try. The evidence has been gathered patiently across decades by hundreds of researchers. It tells a story that is consistent, documented, and impossible to ignore. And it leads to a conclusion that will change how you think about Mars forever. That conclusion waits for us in the next act. And it is closer than you think. Chapter 8. 3 Futures for the Body That Leaves Earth. we've arrived at the place where science offers not one answer, but several. This is honest. This is how real research works. When the data is incomplete, competing theories emerge. Each one carries evidence. Each one carries uncertainty. Let us meet them gently. The first theory is the threshold theory. This idea proposes that there is a minimum gravity level below which the human body cannot maintain itself. Above that threshold, bones stabilize, muscles retain function, and the cardiovascular system holds its shape. Below it, decline is inevitable. The critical question is where the threshold sits. If it sits at, say, 20% of Earth's gravity, then Mars at 38% would be sufficient. The body would stabilize. Bone loss would halt. Muscles would find a new equilibrium. Return might remain possible. But if the threshold sits at 50 or 60%, then Mars falls below it. The body would continue to deteriorate, just more slowly than in microgravity. The decline would be gentler but unrelenting. Over months and years, it would accumulate into something irreversible. The honest truth is we do not know where the threshold is. No experiment has ever tested human physiology at partial gravity for extended periods. The International Space Station operates in microgravity. Earth provides full gravity. The entire spectrum between 0 and 1 remains a vast, uncharted physiological landscape. Some researchers have proposed centrifuge studies on the space station. Short-arm centrifuges that could spin astronauts at various gravity levels and measure the biological response. These proposals have existed for over a decade. None have been fully funded or implemented. The data we need most is the data we have not yet collected. This is the frustrating beauty of the threshold theory. It could save Mars missions or condemn them, and we simply do not know which. The second theory is the adaptation plateau theory. This model suggests that the body does not simply decline in reduced gravity. Instead, it adapts. It reaches a new equilibrium, a plateau, where bone density, muscle mass, and cardiovascular function stabilize at a lower but functional level. Under this theory, a Mars resident would lose some bone density during the first months. Then the loss would slow and stop. The body would settle into a Mars-appropriate configuration. Lighter bones, smaller heart, thinner muscles. Different but functional. The appeal of this theory is that it mirrors how the body adapts on Earth. Move to high altitude and your blood chemistry changes, then stabilizes. Begin an exercise program and your muscles grow, then plateau. The body seeks equilibrium. If this theory is correct, Mars settlers could live indefinitely on Mars in good health. Their bodies would simply be calibrated for a different world. The cost would come only if they tried to return to Earth's stronger gravity. Their Mars-adapted bodies might not survive the homecoming. Bones too thin for Earth's pull. Hearts too small for Earth's demands. The return trip itself, 7 months in microgravity, would weaken them further. Landing on Earth could be medically catastrophic. The adaptation plateau theory does not say Mars is impossible. It says Mars is one way, a distinction that carries enormous weight. The third theory is the cascading failure theory. This is the most concerning model. It proposes that the various physiological changes in reduced gravity are not independent. They interact, they amplify each other. Bone loss affects calcium levels. Calcium imbalance affects heart rhythm. Heart changes affect blood flow to the brain. Brain changes affect coordination and decision-making. Poor decisions affect safety. Each system's decline nudges other systems toward their own decline. The cascade is slow at first, then it accelerates. Eventually, the body crosses a point of no return. Under this model, time is the enemy. Short stays on Mars might be survivable, but extended stays, years or decades, would trigger cascading interactions that no single medical intervention could address. The body would become increasingly fragile across multiple systems simultaneously. The cascading failure theory is supported by some evidence from long-duration spaceflight. Astronauts returning from year-long missions often report multiple simultaneous health changes: vision, balance, bone density, cognitive speed. The problems cluster. They do not arrive one at a time. But microgravity is not Mars gravity. The cascade might be slowed or interrupted by 38% gravity, or it might simply run on a longer timeline. Again, without partial gravity data, the theory remains plausible but unproven. Each of these three theories leads to a different future for Mars exploration. If the threshold theory is correct and Mars sits above the threshold, then round-trip missions are possible. Crews could visit and return. Mars becomes achievable in the traditional sense. This is the optimistic scenario. If the adaptation plateau theory is correct, Mars settlement is possible, but return is not. The mission design shifts from expedition to emigration. Volunteers go knowing they stay. Humanity expands, but the cost is permanent departure. This is the bittersweet scenario. If the cascading failure theory is correct, even long-term settlement may be threatened without significant medical intervention. Living on Mars might require constant pharmaceutical support, artificial gravity supplements, or genetic modification. This is the challenging scenario. All three theories are currently active in the scientific literature. None has been conclusively proven. None has been eliminated. They coexist, each with supporting evidence and significant gaps. And somewhere inside this trio of possibilities lives the actual future. The one real outcome that physics and biology will eventually reveal, whether or not we are prepared for the answer. But there is new science emerging right now, new instruments and new experiments that may soon narrow these possibilities dramatically. That science is where we turn next, into the laboratories and observatories where the question of Mars is being quietly, patiently pursued. Chapter 9. The instruments that will write the answer somewhere on Earth tonight. A machine is listening to the universe with a sensitivity that would have seemed magical a generation ago. New instruments are changing what we can measure, and what we can measure determines what we can understand. The James Webb Space Telescope floats at a point in space called L2, about 1.5 million kilometers from Earth. It sees in infrared. It peers through cosmic dust. It studies the atmospheres of distant exoplanets, reading their chemical signatures. Why does this matter for Mars? Because Webb and telescopes like it are teaching us how to read atmospheres, how to detect gases that indicate geological activity, water cycles, and potentially even biology. These techniques, perfected on distant worlds, will be turned inward toward Mars with increasing precision. We already know Mars's atmospheric composition, but the dynamics, the seasonal flows, the subsurface gas exchanges, these are still being mapped. New orbital instruments around Mars are measuring methane spikes that appear and vanish without clear explanation. Methane on Mars is a puzzle. On Earth, methane is produced primarily by living organisms and geological processes. Mars appears to release methane periodically. The Curiosity rover has detected it. The European Trace Gas Orbiter has struggled to confirm it from orbit. If Martian methane is biological, the implications reshape every Mars mission plan. If it is geological, it tells us about subsurface chemistry that could affect habitat construction, resource extraction, and long-term human safety. Either way, the answer matters enormously. But the instruments that may matter most for the human question are not telescopes. They are biomedical. NASA's Human Research Program has spent decades studying astronaut health. New technologies are emerging that could transform what we know. Organ-on-a-chip devices, tiny microfluidic systems that simulate human organs, can now be exposed to simulated Martian conditions. These chips contain living human cells arranged to mimic the function of a heart, a lung, a bone, a brain. Researchers can subject them to reduced gravity simulations, radiation exposure, and altered atmospheres. The results are not perfect proxies for whole-body responses, but they are far better than anything we had before. Recent organ-on-a-chip experiments have revealed that cardiac cells behave differently under simulated reduced gravity than predicted by older models. The cells change their beating patterns, their electrical signaling shifts. The implications for long-term heart health on Mars are still being analyzed. Simultaneously, ground-based bed rest studies continue. Volunteers lie in beds tilted 6 degrees head down for weeks or months, simulating some effects of microgravity on fluid distribution. These studies are imperfect but revealing. They show how quickly the body begins to change. New bed rest protocols now include partial weight bearing to simulate lunar or Martian gravity. Early results suggest that even small amounts of gravitational loading make measurable differences in bone preservation. This is encouraging for the threshold theory, but the studies are still young. Here is a quiet revelation that arrived recently from an unexpected direction: the study of twins. NASA's famous twin study compared astronaut Scott Kelly, who spent nearly a year on the space station, with his identical twin brother Mark, who remained on Earth. The results, published in 2019, were landmark. They showed changes at the genetic level. Scott Kelly's telomeres, the protective caps on chromosomes, lengthened in space, then shortened rapidly upon return. His gene expression changed. His gut microbiome shifted. His cognitive speed declined slightly. Most changes reversed after return to Earth. Some did not. The twin study was a sample size of one pair. It cannot be generalized broadly, but it opened a door into understanding spaceflight at the molecular level. Future studies with larger groups could reveal patterns that one pair cannot. And here is where a paradox emerges in the new data. Some biological changes in space appear protective. Telomere lengthening, for instance, is usually associated with cellular youth. Some immune responses become more active. Certain gene expression patterns shift in ways that resemble stress responses, which can be strengthening in small doses. The body is not simply degrading in space. It is responding, adapting, fighting. Some of those adaptations might be harnessed. What if the very changes we fear could be guided, managed, turned into tools for survival rather than markers of decline? This is the frontier of space medicine. Not just documenting damage, but understanding response. Not just measuring loss, but mapping adaptation. The distinction is subtle and profound. It changes the question from can we survive to how will we transform. New gravitational wave detectors, while designed for astrophysics, are pushing our understanding of gravity itself. LIGO and Virgo detect ripples in spacetime from colliding black holes and neutron stars. This fundamental research seems distant from Mars medicine, but understanding gravity at its deepest level informs everything about how mass and biology interact. If we discover new aspects of gravitational physics, the implications could cascade into medicine, engineering, and habitat design in ways we cannot yet predict. The extremely large telescope, currently under construction in Chile's Atacama Desert, will be the largest optical telescope ever built. Its mirror will span 39 meters. It will see planetary surfaces with unprecedented clarity. Mars, when visible, will reveal details invisible to current instruments. But more importantly, the ELT and instruments like it represent a philosophy. The philosophy that answers come from better observation, that patience and precision eventually dissolve mystery, that the universe yields its secrets to those who build careful enough tools and wait. The answer to whether Mars settlers can return to Earth will not come from a single dramatic experiment. It will emerge slowly from accumulated data, from organ chips and bed rest studies and twin comparisons and atmospheric readings and radiation measurements. It will come from patience, which is perhaps the most human instrument of all. And that patience is leading us now toward the central question of this entire documentary. The question we posed at the very beginning. The promise we made to you as you settled in for this journey. The answer is ahead. It has been taking shape through every chapter. Through bone density data and Kepler's ellipses and Babylonian clay tablets and the twin study. All the threads are converging now, gently, toward the same quiet conclusion. Let us go there together. Chapter 10. The truth that was always waiting. We began this journey on a launch pad at 3 in the morning. You were wearing a spacesuit. The rocket was taller than a cathedral. And I told you that stepping inside would mean you would likely never return to Earth. Now it is time to explain exactly what that means. Not with fear, not with drama, but with the calm clarity that the truth deserves. Because the truth, when you sit with it long enough, is not frightening. It is profound. Here is the revelation, assembled from decades of evidence. The human body is not a fixed thing. It is a conversation, a continuous, dynamic negotiation between your biology and your environment. Every moment, your cells are listening to the world around them and adjusting. Gravity speaks. Your bones answer. On Earth, this conversation has been running for 4 billion years. Your body's responses are ancient, refined, deeply optimized. They expect Earth. They are calibrated for Earth. They function best on Earth. This is not opinion. This is evolutionary fact. When you leave Earth, the conversation changes. Your cells hear a different voice. In microgravity, they hear silence where gravity used to speak. On Mars, they would hear a whisper where they expected a shout, and they would respond accordingly. The response is adaptation. Your body would genuinely adapt to Mars. Bones would thin to match the lower mechanical demands. Muscles would shrink to the size Mars requires. Your heart would remodel to pump blood against a weaker gravitational pull. This adaptation is real and measurable. It follows predictable biological pathways. It is not damage in the traditional sense. It is your body doing exactly what it evolved to do, responding to the environment, fitting itself to the world it inhabits. And this is the key that unlocks everything. Adaptation is not reversible on command. You cannot simply decide to unadapt. You cannot board a return rocket and expect your Mars-calibrated body to remember Earth. The conversation has moved on. Your cells are listening to Mars now. Earth's voice has become unfamiliar. After 1 year on Mars, your bones would be measurably thinner. After 2 years, significantly so. After 5 years, your entire musculoskeletal system would be calibrated for a world with roughly 1/3 of Earth's gravity. Going back would be like tripling your body weight overnight. Your heart, now sized for Mars, would struggle to pump blood upward against Earth's pull. Your blood pressure regulation, adapted to gentler demands, would falter. Standing up on Earth might cause you to faint. Walking might fracture bones that Mars had quietly hollowed. And the 7-month return journey in microgravity would weaken you further before you even arrived. You would land on Earth in worse condition than when you left Mars. The homecoming would be medically dangerous. Perhaps survivable with extreme medical support. Perhaps not. This is not speculation. This is extrapolation from confirmed data on microgravity exposure, extended to partial gravity using the best models available. The models disagree on timelines. They agree on direction. The direction is one way. Here is the revelation, stated plainly. Nobody who goes to Mars will never come back because of a single dramatic reason. Not because of one catastrophic failure. Not because the rocket cannot make the return trip. Not because of one terrifying medical condition. They will never come back because of 1,000 tiny adaptations, each one small, each one logical, each one the body doing exactly what it is supposed to do. A slight thinning of bone here, a minor cardiac remodeling there, a subtle shift in fluid dynamics everywhere. Individually, each change is manageable. Collectively, over months and years, they add up to a body that belongs to Mars, A body that has been claimed by another world. Not violently, not suddenly, but completely. The word never in our title does not mean cannot in the engineering sense. It means the body will have changed so fundamentally that return becomes a medical crisis rather than a homecoming. It means that Mars does not take you prisoner. It adopts you. And adoption, in biology, is permanent. This is why anybody who goes to Mars will never come back. Not as the person who left. The Earth-calibrated body that stepped onto the rocket will no longer exist. In its place will be something new. A Mars-adapted human, still human, but different. Beautifully, irreversibly different. And here is where the fear transforms into wonder. Because this is not a tragedy. This is evolution happening in real time. This is the human species doing what it has always done, changing to fit the world it inhabits. Just for the first time, that world is not Earth. The first Mars settlers will be pioneers in the deepest biological sense. Not just the first to walk on another planet. The first to become something new. The first generation of a human lineage that will grow and change and eventually look up at a pale blue dot in their sky. And they will know that dot is where their story began. They will tell their children about rain, about oceans, about the sound of wind through trees. These descriptions will become legends, then myths, then ancient stories that Martian children half believe. The way we half believe stories of gods and dragons. Earth will become Mars's mythology, and Mars will become Earth's greatest act of courage. The people who go will know all of this. They will have read the medical data. They will have understood the bone density charts and the radiation models and the cardiac remodeling projections. They will know the contract they are signing, and they will sign it anyway, because some part of being human has always been willing to trade safety for meaning, to walk into the unknown carrying nothing but curiosity and the hope that what we find will be worth what we leave behind. That is the truth that was always waiting at the center of this story. Not a warning, not a tragedy, a transformation. The most profound transformation our species has ever undertaken. Chosen freely, entered willingly, permanent and sacred. Mars will change us. That was always the point. And so we rest. The journey has been long. From Babylonian tablets to bone density scans. From Kepler's ellipses to the quiet remodeling of a human heart. The story of Mars is the story of what we are willing to become. Tonight, as sleep approaches, feel the Earth holding you. That ancient, patient gravity. That magnetic field wrapping around you like a blanket. This world made you. Every atom in your body was forged in stars and assembled here on this pale blue world. Somewhere above you, Mars is drifting along its orbit, rust-colored and silent, patient as only a planet can be. It is waiting, not with malice, not with hunger, with the quiet indifference of a world that does not know we are coming. But we are coming, and when we arrive, we will not come back. We will become something new, something brave and fragile and extraordinary. And the story of that becoming will be the greatest chapter our species has ever written. Sleep now. Let the stars turn. Let the questions breathe. And if you would like to continue these journeys through the quiet wonders of science and cosmos, subscribe to Science Asleep. We will be here whenever the night feels large and your curiosity feels infinite.